speaker of the morning, Luis Jorge Sánchez. He's from Morelia, and he's going to talk us about the Whitehead group of the Hilbert modular group.
Does everybody speak Spanish?
¿Hay alguien que hable inglés aquí? Todos en español, ¿no? Ah, puedes hablar.
Pues yo creo que puedo hablar en español, ¿verdad? Digo, no tengo problema con darle en inglés, pero me sentiría raro.
Va a quedar en YouTube, sí.
Ah, ok, no, entonces lo doy en inglés.
Perfecto, o sea,
para que repite.
inglés tiene más llegada.
Va a tener más punch. Sí, sí. Well, so I switched to English. Well, you shouldn't say to me that this is going to YouTube. I'm really nervous. Well, so I'm talking about the Whitehead group of the Hilbert modular group, but actually I'm going to talk also about some other things I did in my PhD thesis. Okay, so this is almost what I said in my PhD defense. So let's see. That was 1 month ago. So in this talk, I'm interested in computing Whitehead groups of the Hilbert modular group, and the main tools I'm going to use is the K-theoretic Farrell-Jones conjecture and the p-chain spectral sequence. So this is the K-theoretic Farrell-Jones conjecture, and what the Farrell-Jones conjecture predicts is that this assembly map is an isomorphism, right? So what is this? I mean, what all these things mean? This is the algebraic K-theory of the group ring. This is the group ring. This is the algebraic K-theory. This is a classifying space for the family for the actions of liquid virtually cyclic isotropy. These are the coefficients. The coefficients is the non-connective algebraic K-theory spectrum defined as Davis and Luke, and this is a suitable homology theory. And this assembly map is the map induced by the projection from the classifying space to the one-point space, right? This is also a suitable equivariant homology theory. Okay. So what the Farrell-Jones conjecture predicts is that this arrow is an isomorphism. And this way, once we know that the Farrell-Jones conjecture is true for some group, we can use this isomorphism to compute these algebraic K-theory groups that are, in general, they are difficult, really difficult to compute. But on this side, we have a homology group of a classifying space. I mean, a homology group of a CW complex. And in theory, it's well, you have more tools available to attack this computation. You have spectral sequences. You have major arbitrary sequence. So, in theory, at least in theory, this is not as scary as this one, right? And what the Farrell-Jones conjecture says is that the algebraic K-theory of this group ring is determined by the algebraic K-theory of these group rings, where V is a virtually cyclic subgroup. I mean, a group that has a finite index cyclic subgroup, finite or infinite, and a CW structure of this model. I haven't defined this yet, but I'm going to define it later. So it is worth mentioning that the Farrell-Jones conjecture is motivated by some other conjectures, outstanding conjectures. I mean, Farrell and Jones were working, in the beginning they were working in the Borel conjecture. So they wanted to verify the Borel conjecture at least for some geometrical, some important geometrical cases, such as fundamental groups of manifolds with some hypothesis in the curvature, the scalar curvature. So they started to work, and they, after like 25 years of work in this problem, they get to this conjecture. I mean, they reduce the problem of many other conjectures, the Borel conjecture, the Navikov conjecture, and some others, to these assembly maps. Okay, so the Borel conjecture that has to do with the topology topological rigidity of spherical manifolds. I mean, the Borel conjecture predicts that if you have two spherical manifolds with isomorphic fundamental groups, then actually your manifolds should be homeomorphic, right? And the Navikov conjecture, that is a little more complicated to state, but it has to do with the homotopical invariance of certain higher signatures. So the K-theoretic, I mean, in this talk I'm just talking about the K-theoretic, but there is also an analog L-theoretic Farrell-Jones conjecture, and both of them imply the Borel conjecture. The L-theoretic implies the Navikov conjecture, and also this Farrell-Jones conjecture is a generalization for some other conjectures, like the Bass conjecture, the Kaplanski conjecture, that I'm not a real expert in this conjecture, so I'm not saying a lot more about them. And also implies the vanishing of the classical Whitehead group for torsion-free groups. So if you have a group and the Farrell-Jones conjecture, the K-theoretic Farrell-Jones conjecture is true, then and your group is torsion-free, then this Whitehead group is vanishes. So, I mean, I performed some computations of the Hilbert modular group, but obviously, as you can see in my talk and in my presentation, what I'm really interested in is in the Farrell-Jones conjecture, not that much in the Hilbert modular group. So I'm talking more about the Farrell-Jones conjecture than the Hilbert modular group. So this conjecture has been verified for a great amount of families of groups. Usually these groups have like intrinsic geometry. So it is known to be true for word hyperbolic groups in the sense of Gromov, for cat-zero groups, for linear groups, also for S-arithmetic groups, for these bound-like solitary groups. Also, it's being verified in the for pure and full break groups on any surface, and for general lattices in virtually connected Lie groups. And for this work, this is particularly important because as a particular case of this, we have that the Farrell-Jones conjecture is true for the Hilbert modular group. So we didn't verify the Farrell-Jones conjecture. We used the Farrell-Jones conjecture that is known to be true for these groups, and then perform some computations. So I'm going to define what a classifying space is. I mean, here in the Farrell-Jones conjecture, you have a classifying space. So I'm going to say what do I mean by a classifying space. So if we have a group that, maybe I didn't say this at the beginning, but all groups that I'm taking into account are discrete groups, or at least I'm thinking in discrete groups. So if I have a group G, a family of subgroups is a collection of subgroups of this group G that is closed under conjugation and under taking subgroups. So we have these examples. These are examples of families that you can define for any group. The family that consists only of the trivial subgroup, the family of finite subgroups, of this family of finite bicyclic subgroups that it is not really famous. The family of virtually cyclic subgroups. I don't know if this is very famous, but at least for me it is. So, and the family of all subgroups. I'm particularly interested in this one, in this part of the talk, but in our computations, the families that play an important role are this one and this one. So let's see. So a classifying space for a group G and a family of subgroups is a GCW complex. I mean, a CW complex with an action of G, such that the action is nice, and such that all isotropic groups belong to the family, that's why I ask for the family to be close under conjugation or under taking subgroups. And all fixed point sets are contractible, right? So the theorem is that given any G and any family, you always can construct a classifying space. The proof of this theorem is constructive. I mean, you, given the group and the family, you construct a model, an explicit model. The problem with this construction is that the model you get is huge. It's infinite dimensional, and also this exists and it is unique, but up to G or mod P. So you may construct like two different, given G and F, you may construct two different classifying space, I mean two different models, and they may have different dimensions, because the dimension is not a homotopical invariant. So this is what I just said. And the minimal dimension where the classifying, I mean this is G, sorry, where the classifying space occurs, it's called the geometric dimension. This GD stands for geometric dimension. So also, if we have two families, the first one contained in the second one, it is interesting to ask how these geometric dimensions are related. In general, there is not a general relation. I mean, this shouldn't be lower or equal than this, or this shouldn't be equal in general, or the other way. All cases hold in something. Well, so some of the things I did in my PhD thesis, I get this result. If you have this family, and maybe I should say that these families are contained in each one is contained in the following one. I mean, this is contained in this, and this is contained in this. So I'm interested in this inclusion. I mean, this FBC is contained in BASIC. And then I asked to myself how these geometric dimensions can be compared. And what I got was that, well, you have two cases, that these two families are equal. In the case that these two families are equal, you don't have an interesting question. I mean, they are equal, and the geometric dimensions obviously are equal. But if this is properly contained in this one, then what I got is that this geometric dimension should be infinite. I mean, any classifying space for G respect to this family should be infinite dimensional. So this is interesting because in the Faraday-Jones conjecture, it was proven. I didn't write it down in my slides, but in the Faraday-Jones conjecture, this family is the one that appears. I mean, you need a classifying space for this family, but you also can replace the family, this family, by this one that is essentially smaller. And so, from the computational viewpoint, you may ask, well, what if I, instead of using a classifying space for this family, what if I use a classifying space for this family that is smaller? Well, this result, what it says is that maybe it's not easier to use. It is not smarter to use this one than this one, because if you use this one and it's different from the classifying space of respect to the family of virtualistic subgroups, then your classifying space is infinite dimensional. I mean, it's huge. So you are not simplifying things by using this smaller family. I mean, I think that that's why it's interesting, this result. So since it is not easier to use this family, well, so I get back to this one. So to the classical case. Now I'm going to define the Whitehead group, at least the classical one. But later on in the talk, I'm going to talk about more Whitehead groups. So let G be a discrete group. So we may associate to this group its group ring, and we may define this general linear group. This is the group that consists of all matrices of finite size, and then you put a tail of ones in the diagonal. So you can multiply matrices of different size. And I define this K1 group as the abelianized of this general linear group. I mean, is this general linear group module the commutator subgroup. And the Whitehead group is the quotient of K1 by these elements that you may think the elements of G as 1 by 1 matrices, right? So you have these elements naturally in here, and so you have them in here. So this quotient makes sense. And as motivation, the Whitehead group is relevant at least in algebraic topology because it's a natural home for some obstructions, such as the one that appears in the statement of the Escobordism theorem. This is essentially the Escobordism theorem. You have a bijection from diffeomorphism classes. I should you define what diffeomorphism means, and then you have a bijection from diffeomorphism classes of H cobordisms over N, and the Whitehead group of its fundamental group. And this is also, well, and this theorem is important because essentially because it's one of the main tools in the theory of classification of manifolds. Examples. I mean, I defined the Whitehead group, so I want to say a little what is known about this Whitehead group. So I put some examples. So the Whitehead group vanishes if G is trivial. This is not very difficult to verify. It's like linear algebra. Maybe I didn't say it, but one element here vanishes. It's in the class of the identity matrix. I mean, it represents the zero element. If you may you may take this matrix to the identity by some row and column operations, elemental operations. So this may be verified by just using linear algebra, and also this vanishes if G is a cyclic group of these orders. If G is free abelian, and this is a theorem. I mean, this is not that easy to verify. And also G is this Whitehead group vanishes if G is either the fuel of the pure braid or the pure braid group over any spherical. I mean, this is a spherical surface. So this is also a theorem. And this is the conjecture that I was talking before, right? If your group is torsion-free, then this Whitehead group should vanish. What else do we know about the Whitehead group? Well, we know that the Whitehead group of this cyclic group of order 5 is isomorphic to the integers. And this has to do with the fact that in the group ring of this cyclic group, you can find units that are not the trivial one. I mean, in a group ring, you have trivial units, right? The elements of the group are invertible, but you may ask if in your group ring there are some other units, and that this is not trivial. It has to do with the existence of non-trivial units in the group ring of this group. So we also know that the Whitehead group of every finite group F is finitely generated. So since this Whitehead group is an abelian group, then now you know that it splits like the torsion part and then torsion part, non-torsion part, and that things that you learn in your group theory course in the licenciatura. Well, so, and also we also know how to compute this torsion-free part of the Whitehead group when G is when you have a finite group. It has to do with the representation theory of your group, right? So it is the rank of the torsion-free part is the number of a reducible real representation of F, that it is highly computable if you know really well your group. You may compute this number by counting conjugacy classes and minus the number of rational irreducible representations, and you can compute also this number by counting conjugacy classes of cyclic subgroups of F. And also, if G is a function group, then we know that the Whitehead group of G splits as a direct sum of Whitehead groups of where this sum runs over the conjugacy classes of finite maximal subgroups, and this is a theorem by Berkowitz, Pineda, and Pearson. And I'm interested in this theorem because it's the prototypical result of what I did in my PhD thesis. So I'm going to define now the Hilbert modular group, and now you consider finite extension of the rational numbers, and we say that K is totally real if all the embeddings of K in the complex numbers have image contained in the real numbers. So denoted by O sub K, it's ring of algebraic integers, and by definition the Hilbert modular group is this one. Are matrices of size 2 by 2 and with coefficients in the ring of algebraic integers of this totally real finite extension of the rationals, right? The prototypical example of the Hilbert modular group is you take SL2 Q where D is positive and score free. So this is no, I mean you take K equal to this one. That's right. So what we proved is a theorem with the same flavor of that one of Berkowitz, Pineda, and Pearson, and is that, maybe I should say that function groups and the Hilbert modular group both live in SL2R. I mean, they can be seen as isometries of the hyperbolic plane. But the essential difference between them is that these are lattices, and the Hilbert modular group are not. So this is a different case. I mean, the case of the Hilbert modular group is not covered in this theorem. So we prove this, that it says essentially kind of the same of the theorem of Berkowitz, Juan Pineda, and Pearson. And we also prove this. I mean, here I'm dealing with the projectivized version of the Hilbert modular group, right? And here I'm dealing with the Hilbert modular group. I mean, this is what I wanted to compute. So what we proved is that this Whitehead group is isomorphic to this K-theory group, where in this side you have the Hilbert modular group, and in this side you have the projectivized Hilbert modular group. And also we prove this, that this, I mean, well, maybe I should say that this Whitehead sub 1, it is what I defined. I mean, this is the classical Whitehead group, this one with the sub-index 1, and these are some other groups, but the results that we got involves also the other Whitehead groups. So what we prove is that this Whitehead group splits as a sum, where you have also the Whitehead group of the projectivized version, the abelianized of this group, and a copy of the integers mod 2, and you have also these splittings. And also, well, these results are in this rank. I mean, for Q here, for sub-index lower or equal than 1. But also we computed this one. I mean, the torsion, the non-torsion part of these K groups, and we did this for any Q. I mean, not only for the lower Whitehead groups or the lower K theory. We did this for any Q in the integers. And all these computations of ranks are in terms of representation theory of the maximal, the maximal finite subgroups, where this R is the number of real irreducible representations of M, and this C is the number of real irreducible representations of complex type. This is the same, but for the p-adic numbers, and this is for the field of p elements. All these numbers are highly computable because all finite subgroup of the Hilbert modular group are cyclic. So all these are highly, really computable. So this is really explicit. If you have one example of K, and you are able to compute the orders of the order of any maximal subgroup, finite maximal subgroup, then you are able to compute all of this. Well, as I said, what we used was the K-theoretical Fourier's conjecture that was proved by Camello, Rupping, and Luke, as I said before, the p-chain spectral sequence, and also I used the action of SL2R and PSL2R in the hyperbolic plane. So I'm going to sketch the proof of this theory, right? So you may take this as a definition. I mean, this is a theorem of Badhausen, but you may take it as a definition for our purposes. So you define the Whitehead group as this homology group, and then our task is to compute this homology group using the p-chain spectral sequence. So, if one corollary of the Faradian's conjecture is that this Whitehead group is isomorphic to this one. I mean, you take here the mapping cylinder of this projection, but you may replace this G space by this other G space. That is huge, but it makes things easier since the isotropy is smaller. So in our case, what we did was to reduce this family. I mean, this double bar means that I'm using a classifying space for the family of virtually cyclic subgroups, but I may replace this family of virtually cyclic subgroups by the family of finite subgroups. So this is okay because finite subgroups are easier than virtually cyclic subgroups. So now we have to compute this one. And in this case, when you are dealing only with the family of finite subgroups, the p-chain spectral sequence behaves well. So this is the p-chain. This is an expression for the first page of the p-chain spectral sequence, and here you have Borel homology, and here you have some things that I'm not going to define because I'm not really using this part of the expression. What I'm really using is this index. I mean, the p-chain spectral sequence, in each column you have a direct sum that runs over the p-chains of this category. This category is the orbit category, restricted to the family of finite subgroups. So one way that you can picture this category is in this category you have all the orbits all homogeneous G spaces with isotropy in this family. So here you have like the big orbit, and then here you may have like some other orbits. You have a lot of arrows here. And you have maybe more here. Well, so a p-chain in this category, it is a sequence of arrows like this one, such that the arrows are not isomorphisms. So what we did was to reduce this family even more to a family where you don't have p-chains of length 1 or 2, just p-chains of length 0. So we replace this family with a smaller family, and this way we were able to manage this index, and in this way we were able to prove that this p-chain spectral sequence collapses in the first page. So if this spectral sequence collapses, then we win. So the family that we used was this family that consists of the trivial group and all the maximal subgroups. And this can be done because the Hilbert modular group allows this replacement of the family of finite subgroups with this other family. So here is where we use the action of the Hilbert modular group in the hyperbolic plane to reduce the family. So we ended up with the following E1 term. I mean, you don't have p chains for p greater or equal than that one. You just have well, because in this, maybe I should say what happens with this family. I mean, in this family, NF, you have this one and the orbits of the maximal subgroups. But in this category, almost every arrow is an isomorphism, because since these are maximal, if you have an arrow that goes from here to here, then this should be an isomorphism because of maximality. So the only arrows that are not isomorphism are this one. So this should be a one chain. But since we are dealing with a homology group, that I mean a relative homology group, we should neglect this kind of chains, those that starts in this orbit. So this way we just have zero chains, and so the other terms are zero. I mean, the index is empty, and we just computed these terms, and these terms were the Whitehead groups. So that way we computed these Whitehead groups. Thank you.
Questions?
We have all these families of groups for which the Farrell-Jones conjecture is verified. I mean, when do you stop? I mean, you can find 20 more families. I mean, it's a bit of an imprecise question, maybe.
Yes.
But
Perhaps form of answer was that any question about groups which you can pose is either trivial or hard, in a way. And the Farrell-Jones conjecture is a statement about groups, in a way. It's more like an excuse to ask geometric families of groups what are the right properties to know about them.
right. But I mean, it kind of looks like a certain industry. I mean, you take a family of groups, you
Yes.
verify the Farrell-Jones conjecture, you go to the next family of groups.
Yes. What I think that they are guided by the universe of Bryson of finitely generated, because actually this Farrell-Jones conjecture is a conjecture for any group, finitely or not finitely generated, but it was proved that this Farrell-Jones conjecture is closed under arbitrary limits. So if you are able to verify the Farrell-Jones conjecture for any finitely generated group, then you are done. So I think that these guys are using like this picture of Bryson's universe of finitely generated groups, and they are doing case by case. I think so, because actually they already verified this conjecture for if you have seen this Bryson universe. Here are finite subgroups, and in this way you are like, I don't know, free, hyperbolic, cat zero, and they kind of already done like this. And in this way you have nilpotent, solvable, and amenable. So they already did this, and also this, and maybe the important case open is this one, and here in the middle I don't know what they have done, but what I think that they are doing is they took this picture and they are doing all the important cases.
That answers my question.
I have a more simple question. Is there geometrical interpretation of the decomposition you wrote there of the Whitehead group. For example, take SL2 zeta.
Yes.
Can you see that the composition of the Whitehead group in your maximal subgroups in a geometrical way? Maybe not, but if you know some way to do it.
No, well, actually, all this is very geometrical. I mean, you take like a model for the classifying space, and then you have like a geometrical model for this lattice structure of the groups embedded in your big group. But I don't know.
For example, I'm thinking PSL2 zeta, the tessellation generated in the
Yes.
hyperbolic disk that gives you the modular orbital.
Yes.
Can you see that decomposition at the level of the modular orbital or something like that? I don't know.
Well, actually, I don't know if this answers your question, and I think it doesn't. But these isomorphisms are induced. All these isomorphism. Well, this isomorphism is induced by the inclusions of the maximal groups in your big group. Maybe I don't know. Yes.
Okay, well, thank you.
Yes.
Other questions? Well, we thank the speaker again. And the next lecture will be given at the 1:30.